Good afternoon, everyone. Welcome back. Hope you enjoyed your lunch breaks and Teresa's keynote a little bit ago. We're about to get started. Just wanted to remind you all first to make sure you silence your phones. And remember to fill out the evaluation for this session afterwards. We really covet your feedback. I want to introduce Ray Chang and Sandy Hyder for this session on serverless architecture. Thank you. Welcome them.
Good afternoon, everyone. So I hope everyone's enjoying Summit so far. Thank you very much for dropping by for this discussion about serverless architectures. I'm Ray Chang, the AWS Solutions Architect, and with me is Sandy Hyder, lead developer for a very cool project, which he'll tell you a little bit more about in a little bit, called BossDB over at Johns Hopkins University. So by way of signpost, excuse me, some of the things we'll be talking about today is basically I'm going to be establishing a baseline, laying down groundwork for what it is that we actually call serverless compute here at AWS. And then Sandy will be here to give you a deep dive into a really cool use case that one of our customers has been able to implement with the technology. So what actually is this thing called serverless? So of course, at the end of the day, there is an actual server running your application code, but a lot of this follows on from one of the core value propositions. If you heard us talk about the AWS platform, which is this idea of subsuming undifferentiated heavy lifting, right? So in the application development and compute paradigm, what this means is the thing that differentiates your organization and your mission and mandate from maybe other services or teams and even your same agency or organization is, at the end of the day, that unique business logic that you have to implement and fulfill for your mission. So the value prop of serverless computing at AWS is to get you, the customer, to be able to focus more of your time and energy on that unique logic to differentiate your mission without worrying about things like provisioning compute infrastructure underneath, right? The promise of serverless compute is to get you out of the business of spinning up or tearing down virtual infrastructure, or in some cases, if you experience things like peaks or valleys in your traffic pattern or your application's demand pattern, right? The other really good value prop of serverless at AWS is to get you out of having to manage that scale in and scale out to keep your application cost efficient and performant. Finally, there's another very important cost optimization capability in serverless, which is, you see that heading there, pay for value. So one of the really interesting attributes of serverless is to allow customers to decouple the cost of your solution from the footprint of that underlying compute infrastructure, right? When your cost is coupled to that infrastructure, you're paying for that infrastructure whether your application is sitting completely idle, or in which case you're essentially paying for infrastructure that's underutilized, or whether your application is experiencing really heavy demand, in which case you're paying for that same infrastructure but also possibly degrading the user experience due to increased latency, et cetera. So a very fundamental and integral attribute of serverless is to more closely tie the cost of your solution to actual volume, right? Requests per second, or total requests serviced if you're running an API or something like a website, right? Actually tie your cost closer to the value you're actually getting out of the solution. And of course, because you as a customer, your input to your solution is defining that business logic and behavior and characteristics that you want it to have. The underlying implementation is on AWS teams to implement. So you get all those best practices rolled in of reference implementations of highly available, secure, fault-tolerant services on AWS. So this is sort of a view of a lot of the offerings in the AWS platform. They're organized here approximately to give you a view of one way to view them on the spectrum from services that are actually running on customer deployed and managed EC2 infrastructure. EC2 is Elastic Compute Cloud. That's one of our core foundational services for running virtual machines on demand at scale. And there are a lot of customers successfully running workloads directly on EC2. But of course, that also means customers are doing things like provisioning virtual machines, making sure security patches are up to date at the virtual operating system level, et cetera, et cetera. So there's some other services there where you start migrating to the other side. In the middle, there's sort of this category which has been labeled managed services here, where the underlying platform is still EC2, but now customers are more in the realm of just consuming the service on EC2 without having to directly manage it, right? So for those of you that have consumed services before, like some of the examples up there are Amazon RDS, which is relational database service. That's a great example of a relational database engine that runs on AWS managed compute infrastructure, but you as a customer don't have to worry about things like OS patches, et cetera. You just get super user privileges at the database level and manage the service accordingly. Finally, all the way in the serverless end, that's primarily what we're here to talk about today. That is, in my opinion, sort of the natural evolution of consuming higher value services in the stack, where you as the customer no longer, I mean, you still have visibility into the behavior of your solution, obviously, but you're no longer in the realm of managing the infrastructure whatsoever, and you're subsuming that, or you're allowing AWS to subsume that undifferentiated heavy lifting. Beg your pardon. So this is another way to kind of view what we're talking about here in terms of value proposition of shifting more towards serverless offerings in the platform. So this view is a little bit more compute-centric around the offerings. At the bottom of that arrow, you see more of what we were talking about, running directly on EC2 infrastructure. Towards the top of that scale is where we have our serverless offerings, which in the compute world mostly center around AWS Lambda, which is our serverless function as a service offering. We'll be drilling a little bit more into that in just a moment. One thing that this chart is meant to explicate is these two columns of different items of operational responsibility. As we said, the value prop of serverless is to try to get AWS to subsume more of that operational responsibility. And as you move towards the serverless end, like Lambda, you can see those items start to disappear from the customer end and more of them pop up on the AWS end, right? I don't want to go through every single one of those bullet points, but the general story told is the closer you get to a true serverless offering, the more you're, once again, letting AWS handle that undifferentiated heavy lifting, allowing you as the customer to focus on the stuff that's specific to you as an organization, agency, business, et cetera. So this Lambda thing that we've been talking a lot about, what is it? So at the end of the day, it's a function as a service, is one popular way to describe it. Customers bring their code to the Lambda platform, and AWS executes it. Customers aren't worried about firing up virtual compute infrastructure to run this code. This code can be event-driven. The ideal use cases are short-lived, relatively stateless transactions, and we support a wide variety. Well, so now we support almost any runtime language they can think of, but we'll get into that in a moment, but also some very deep data integrations with the rest of the AWS platform. So aside from the operational responsibility value prop for things like Lambda, it's also a good service to look at from the perspective of increasing the productivity and empowering your application develop teams to get more done, right? So we support, as I said, basically any programming runtime now that you can come up with, just about. But even out of the box, there are some very there are some long-established runtimes that we already supported. Different versions of Python, Node.js, C# for .NET development, Java, Go, Ruby, etc. We also don't want to disrupt the productivity of your existing application processes, so we support essentially the existing popular tool chains out there for application developers to use, IDEs, compilers, etc. And we're going to talk a little bit more about that in just a little bit. So just a few moments ago, I mentioned deep integration with other AWS services. Lambda is, at its core, an event-driven programming platform that permits application developers to start exploring patterns like both synchronous and asynchronous event-driven programming, decoupled microservices, etc. And so this is just a non-complete representation of different services in the platform that can trigger AWS Lambda invocations. And it covers, of course, all sorts of broad spectrums, like you've ingested new data into your simple storage service, or S3 bucket, and you can trigger a Lambda execution based on that event. You've got a code repository persisted up in our AWS code commit service, for example, and we can use that to drive an AWS Lambda execution. So just about almost every use case you can think of, there's a way to use Lambda to run your own custom logic based on that event. So very kind of intermediate level dive into the structure of a Lambda function. Just very briefly here, this is essentially a Node.js code snippet for a Lambda function. Obviously, in practice, your production Lambda functions are going to consist of more code and more complex code than that. But this slide is really meant to drive home the fact that it's a straightforward integration, right? The Lambda execution is triggered by a given event. It's got essentially an execution context that goes along with it, and then you write your custom business logic to act on that event. In the case of Node.js, for example, both the event and the execution context arrive simply serialized as JSON objects, which then your application development process can then deserialize and process accordingly. So some of that developer toolchain integration we mentioned earlier, there's lots of different options available here, and this is, once again, a non-exhaustive list, but we, of course, have our cloud-hosted IDE called Cloud9, but there's also integrations with Eclipse, for example, for your Java developers, or PyCharm if you have Python application developers using that IDE. Last year at reInvent, we announced developer preview for our toolkit integrations with both IntelliJ and Visual Studio Code. Another feature that we also announced at reInvent last year was the availability of Lambda layers. So this is a relatively new addition to the Lambda functionality ecosystem. This is the ability to define layers of code or layers of dependencies in your AWS account that can serve as common execution packages or dependencies for multiple Lambda functions. So this can greatly simplify the process. For example, if you have within your enterprise standardized libraries already for doing things like authentication or generating UUIDs, et cetera, functionality that's going to be widespread throughout your Lambda ecosystem. Instead of repeating the code over and over again, you can now use layers to deploy essentially a common library across that infrastructure. So Lambda integrates very tightly with another service, which I want to touch upon briefly, in the AWS platform called API Gateway. Much like how Lambda is essentially a serverless function execution service, API Gateway is essentially a managed serverless HTTP endpoint provider for you. So instead of rolling out your own compute infrastructure to expose HTTP endpoints for your APIs, for example, you can now deploy it onto API Gateway, and you bring your own logic, you define your own endpoints in well-known formats, for example, like Swagger APIs, or we have, of course, our own AWS APIs for you to programmatically build out those definitions if you wish. And a lot of what we talked about earlier, the management of the infrastructure is not upon you as the customer, so you don't worry about things like provisioning, throttling up and down, scaling in and out for different peaks and valleys in your demand. And, whoa, too fast. So one of the notional ways that API Gateway can play well with Lambda and other services in the AWS architecture is to use API Gateway, for example, to front requests coming in from the general internet. There's some other boxes on there that we haven't really talked about yet, but for example, CloudFront, our scalable content distribution network solution. But this is essentially what you're looking at is you could think of this as a website where the entry point from the general internet, there are no servers there to handle HTTP requests, right? There's no uptime of boxes for you to worry about there to keep your services responsive and available. Now, you could have your services integrate with other workloads that happen to be hosted on other AWS services like EC2 on the back end, but that's completely up to you in terms of freedom to design and implement. Another kind of good service to mention here is step functions, which is a way of coordinating the execution and sort of serialization or serializing execution of multiple lambdas. Step functions, the development of a step function workflow is very intuitive. What you're creating is essentially a finite state machine with a defined start and different transitions to different states, which can tie into executions of your various lambdas. And the whole thing, after it gets built, it will display it to you in a graphical workflow, so it's very easy for you to see what even a fairly complex application workflow involving potentially many, many Lambda functions can look like. And finally, there's a couple other important categories of services for integration here for serverless workflows. Things like security, right? For anyone here that's worked or deployed any sort of workflows into AWS, you've probably had to deal with identity and access management already. And Lambda and API Gateway and step functions are no exceptions. IAM is pretty much where the rubber meets the road in terms of how we control, audit, and permit or deny access to AWS resources. Cognito is a handy, once again, serverless managed user pool that you can use for authenticating your applications and authorizing their access to your backend systems. Other points of integration are with CloudWatch, we mentioned that earlier. That's essentially a content distribution network that you can use to front your services or websites, for example, and reduce end latency to even a distributed geographical user base. X-Ray is a handy tool for troubleshooting or just gaining visibility into end-to-end performance and latency of your workflow, right? So if your users start reporting that certain calls to your services are taking longer than usual, X-Ray is a great way to get instant visibility into where exactly those bubbles or lags could be. So that's sort of a lot of setup from me, and now I want to turn it over to Sandy so he can talk about how Johns Hopkins is doing something really cool with this technology.
Thanks, Ray.
There we go. All right.
Okay, so that was a quick introduction of Amazon serverless computing. What I'm going to do is actually go through some real-world examples using BossDB. BossDB is a neuroscience database for brain research. It provides mechanisms for uploading brain images annotating the data, visualizing it, and then actually individual accessing images, metadata, and objects in the system to do research. It's built entirely in AWS and provides a scalable solution that's highly available. A lot of our back-end services are actually use serverless computing, and we're going to go over some examples of that here. A quick shout out to our sponsors, IARPA and NIH. On the IARPA Microns project, we're actually trying to revolutionize machine learning by reverse engineering the brain. And what we're then going to do is actually try and create neurally inspired artificial intelligence. That was started in 2015, and out of that work, we actually got another new funding from NIH to actually build the community database, BossDB. And in that it's another cloud database where we're actually storing electron microscopy and X-ray microtomography data. And both of these are part of the US Brain Initiative. So quickly about me, I work for the Applied Physics Lab. It's a division of Johns Hopkins University. We have around 6,000 members, 6,000 plus members. It's in Laurel, Maryland, and we work with all of those sponsors down there in that bingo diagram you see. So what I want to do is give you a little more detail about how we actually put data and what data is actually stored in the BOSS, and that'll help you understand how we do then our serverless technologies in future slides. So this BOSS actually stands for Block and Object Storage Service. And the block in this case is a three-dimensional array, which we call a cuboid, and that's a three-dimensional chunk of data that we then store spatially indexed in S3. So in this diagram, you can actually see there's a microscope which is actually taking slices of brain tissue, taking a picture of them. We then chop those down into individual tiles, and then we take 16 consecutive tiles to actually build a cuboid that we store in S3. The other side of the BOSS, Block and Object Store, are objects, and objects are really co-registered identifiers. In this case, they're 64-bit identifiers that are identify objects in the system. So in this case, we're actually identifying different brain cells, and you can see on the left we would actually have the image data. On the right, we've actually identified three objects in the system. And the objects are actually identified as voxels, which is a volumetric pixel, a three-dimensional pixel. All right, so that's objects. So what I want to do now is actually show you how we actually map connections in the brain. So in this example, we have well, didn't do our picture for some reason. Let's see if I go back, if I can get it to run. Oh, well, I'm going to just talk about it. So in this example, we actually were annotating, it's an actual movie where we actually go through individual slice and annotate that same section as it changes slowly over time. And we can then take all those identifiers and actually build up a neuron, and then also map out where the synapses are, which is the connections between neurons. So in this example here, it was small, it was about 1,000 connections, I think. In the microns data set, we actually are using a cubic millimeter of brain tissue, and we end up having millions and millions of connections in there. So it's not something, in this example, they actually hand-coded each one of these identifiers, went through on each image. And we can't actually do that with millions and millions of connections. So we're actually developing algorithms to actually do those annotations for us. And the other thing that's kind of interesting about this is the cubic millimeter we're talking about of brain tissue is actually, if you were to take an MRI of a brain, it would be 1 pixel in that brain, and that ends up being 2 petabytes of data in our system. So here are the ways we actually use serverless technology in BossDB. There's 3 categories, really. Tasks that run periodically. We don't want hardware running all the time in those cases, so we use serverless to do it. Error reporting, it can be very handy to use Amazon SNS to notify you when there's an actual problem in your server. And then managing servers, so when there is a possible issue, we keep them from progressing into larger problems. And so we're going to go over 3 specific examples of using serverless: high-speed ingest, downsample, and HashiCorp's Vault and Console servers. And we'll explain all of those here in just a few. So high-speed ingest. We have several images. The client will have several tiles that they want to actually upload, but that's not the format we end up wanting it in. We want it in cuboids, and we want it stored in S3 in a DynamoDB index of the information. So we designed the system so so users can kick off ingest jobs at any time of the day and we don't have to get involved in the system. And we wanted the system to actually be able to scale up. These data sets can be anywhere from 2 gigabytes to 2 petabytes in size. And lastly, we designed the system to make it so the client's bandwidth will be the end problem in the solution. We want it to scale up until their bandwidth is slowing down the upload. And so what I want to do now is actually go through a diagram of how we ended up originally setting it up, and then we'll talk about some of the problems we came across while doing it. So over on the right is the end goal. We want to actually populate the cuboid index and the cuboid bucket. And then in order to actually do that, though, we're going to need to have temporary storage because the clients are actually uploading images over and over again, and we need to convert those into cuboids. So we have these temporary bucket and index, which holds all the images, and when we get 16, I'm not sure why it's going forward here, and when we actually get 16 tiles in a row, we can actually convert that into a cuboid. So when we first start up, when the client wants to actually start an ingest job, they give us the dimensions X, Y, and Z that they actually want to load, and we then compute all of the tiles that need to get uploaded for the ingest job to actually be complete. So we create a step function and 2 SQS queues, the images to upload and the cuboid ready queue, and then the step function will actually then populate all of the actual messages in the images queue. So we fire off a whole bunch of lambdas in parallel to actually populate all these messages. And then when we actually see afterwards that we have the correct count, we allow the client to actually, I'm going to go back and show you so you can show that one again. All right, so there. So the client now does this loop where it basically goes and grabs a message that tells it what tile it needs. It goes and finds it on its server and uploads it up to the tile bucket. And it continues to do this over and over. And the nice thing about this is now we've got a solution that if the client's system crashes, we know exactly where they are because we've got all the images that need to get uploaded still. The client is actually multi-threaded, so, and it's also, we can actually spin up multiple clients in parallel and actually have them all work on getting this data ingested into our system. All righty. So when a tile is actually uploaded, it automatically fires off a Lambda, which goes ahead and registers that new tile into the tile index, and it checks to see, do I have 16 consecutive tiles, and if so, it actually puts a new message in the cuboid ready bucket. Alrighty. So after it actually does that work, it would then go and actually delete the message out of the image queue. Now a new Lambda is actually fired off of the cuboid ready queue, and it goes and grabs all 16 of those images, converts them into a cuboid, and puts it in the end result of the index and bucket for the system. So this ended up working pretty well for us for about 6 months, and then as we expanded and got faster and faster, and our research associates got better actual network connections, we found out that it actually didn't work so well, and here's the problem that we ran into. So the way we have this working now, the client goes, grabs a message out of the message queue, uploads it to the bucket, the object is triggered, and it then deletes the message out of the object. Well, when we hit our concurrent Lambda limit, I think it defaults to 2,000, you then start throttling, and Lambdas are actually not firing, so they're not actually deleting the messages that are in that image queue. And then those messages then become visible after they time out, and the client then goes and grabs it again, and it repeats work. So we found this wasn't an ideal solution. So we could have just increased the Lambda, and that's actually what we did for the short term, but we ended up redesigning it a little, and I'll show you that in just a second, how we switched it around. The other problem we ran into is we created a DynamoDB global secondary index for the ingest job ID, And that ended up causing a hotspot in a single partition, because every single write into that global secondary index was hitting the same partition. So the way around that was to actually append a random number between 1 and 100 to the ID, and then we're making sure that we're not hitting that one partition over and over again. Okay, so let me show you how our final solution for actually doing high-speed ingest ended up being. So right now we spin up a new queue as well, and that's the tile queue. So now the client actually does this same loop again. It grabs an image from the images queue, and it uploads to the tile bucket. It then goes ahead and actually uploads a new message to the tile queue, and then it goes and actually deletes the message out of the image queue. So the advantage now is even if our lambdas are throttling, we're still deleting message, we're not duplicating work. The other nice thing about this solution is we're actually, we actually can see how backed up our system is. It's more transparent. The tile queue can show us all of the actual messages that are waiting to be to be finished. So at this point, it fires off a new message and really a new lambda, and then at this point, it's really the same as it was working before. So it's really, we're changing it now that the lambdas are firing off the tile queue in the system. Okay, so this is a diagram of actually ingest speeds. So we were able to actually get 200 gigabytes per minute upload speeds when we were actually doing testing. In this testing, we eliminated the client's bandwidth. We actually used Snowball to upload all of the tiles to a bucket, and then from there we did the ingest through our ingest client directly into the Boss. So that was pretty good. And actually the ending was concurrent lambdas was slowing down the system. So we could have gotten it even faster, I think, if we needed to. So I'm going to take a quick minute and actually talk about Heaviside. This is a library, open source library we created for dealing with AWS step functions. It has a DSL, a domain-specific language, and a compiler, and it will actually take your Heaviside code and actually compile it to an AWS step function in JSON format, and it'll actually verify that it is working correctly. What we found is actually working with step functions is really nice, but it can be hard to actually update them over time. So using our DSL, we found it was easier to actually update the code and then compile it down. So I'm going to show an example. Here is our actual delete step functions. Over on the right is the actual step function in AWS. Our delete function is kind of complex because we have a lot of foreign keys and we have to make sure we're deleting them all in the proper order. Over on the left is the example of our delete Heaviside script. It's 48 lines long. It compiles down to 154 lines JSON step function, which can then be imported into AWS. Okay, so now I want to go through an example where we're actually using our step function again, and this is downsampling. So downsampling, after our researchers actually uploaded their data, they oftentimes want to pull back and see the data from farther away, kind of like you would do in Google Maps. Sometimes you're looking at the street level, other times you want to see the state or nation level. You don't want to download all of the streets just when you're looking at the state level. So we create these resolution levels, and you can see in this example, we're taking 4 tiles, 4 cuboids at resolution 0, and combining them into a single one at resolution 1. So this sort of shows the amount of levels we actually typically do. We usually have 6 to 10 resolution levels depending on the data size. And you can see then the size, the extra size that we're actually storing in AWS associated with each of these resolution levels. So when we designed our downsample, we wanted it to be in serverless computing because downsample really only happens like 1% of the time. The researchers are uploading their data, then they want it downsampled, and then they're using their data and actually working with it. So it's not something that happens a lot. We don't want to have hardware around for it. But it does need to scale up very dramatically. So with a 2 petabyte data set, we would actually do 37 million writes to S3 in DynamoDB and 148 million reads to both of those as well. So, and we also want it set up so users can kick this off at any hour of the day, just like with ingest. So what we found with benefits with doing serverless is that we Don't need to have servers running all the time. It'll just automatically kick off. We can actually massively scale up without the administrators getting in the loop, and it's highly available automatically. That's given to us by using these features. Okay, so here is our downsampling solution. We're basically taking 4 cuboids, downsampling them to 1. So in our first down at the bottom, you can actually see the AWS step function, and we have 2 queues, SQS queues, a downsample set and a Lambda DLQ, dead letter queue. So in the beginning, the populate activity actually in parallel populates all of the downsamples that have to actually occur into that SQS for downsample sets. And then when it actually gets them all in, the Lambda checker activity then fires off a whole bunch of Lambdas in parallel. And all it's doing is firing off Lambdas and telling them to go do work. The one thing it does do is it's got a little smarts in there to say, are Lambdas throttling? And if so, they pause for a second, check to make sure Lambdas stop throttling, and then continue on. And at this point, those Lambdas then go grab a message out of the downsample queue, and then they actually go and grab those 4 cuboids that they need to work with and convert them into the cuboid for the next resolution level and write them out to the cuboid index and cuboid bucket. So the way we actually check that everything is working okay is we use that dead letter queue. So if a Lambda actually fails, it will go into that dead letter queue and we'll know that work didn't get done. In the end, the Lambda checker goes back and looks at the dead letter queue, makes sure there's nothing in there, and then it also makes sure there's no more work to be done in the downsample set, and then we know that the work is all complete. So this is a way of taking many millions of operations that need to get run and ensuring that they all get finished in the system. So if I were to actually do this again, AWS has improved things, and they've actually created now so there's an event source. So you can actually tie your downsample set queue, so whenever a message goes in there, it'll automatically fire a Lambda for you. So rather than me having my Lambda checker activity firing off all these Lambdas, it can happen automatically by using this event source and setting it up that way. And the other cool thing about doing it this way is we can actually say, I don't want more than 100 Lambdas to actually fire at once. So you can limit the number of Lambdas that you want to fire in one time, and you can keep it from throttling that way. Okay, for my last example, I want to talk about HashiCorp's Vault and console servers. These manage our secrets in the system. So when our endpoint needs to talk to our RDS database, we don't want to put those passwords in code. We end up sticking them into Vault, and then Vault will pass them out to the endpoint and anybody else who actually needs them. So the thing that's kind of tricky about Vault and console is we can't just stick them in an autoscale group. They need to be running. So console is a distributed database that's used by Vault on the back end, and it's an in-memory database, so we need to have multiple consoles up, and we can't have them all get shut down or we lose our data. So what we ended up doing was devising a solution, which I'll show you in just a sec, but I also want to mention Vault server. It has an issue too. When it first comes up, it actually needs to get fed the keys to unseal and actually be able to get to the data in console. So there's 2 sort of places where the administrators have to get involved in the system. So this is our solution for managing that. We actually, in CloudWatch, we created events that fire Lambdas every 5 minutes, and it then goes and actually does the health check of every server, all 3 of our Vault servers and our console servers. And if there's an issue with any of them, it actually notifies us through SNS. And then the other thing it does is actually hits Route 53, and it changes the weight of DNS to be 0. So when it's set that way, when we have multiple servers with the same name, it will, if the weight is 0, it won't supply those DNS names when somebody requests a Vault or console server. So it's a way of making the rest of the system not use this one piece that's not functioning at the moment. So we found that was a way to keep our servers up and running and not run into a problem of possibly losing all our data. So in the end, I actually want to have a couple takeaways for you all here. And that is that it's very easy to actually coordinate and distribute these components in serverless and create actual microservices. You don't waste resources by actually having servers that are running all the time. It's highly available, and you don't have to have extra resources to have that happen. It's given to you automatically. And it scales massively on demand. As you saw with our downsample, we can just scale up to massive amounts based on the number of lambdas we actually have. And then finally, it's very easy to actually diagnose and debug problems using these systems. So you can sort of build them in, kind of like what we did to manage our servers in HashiCorp. One other thing I guess I wanted to talk about, I'm going to back up one more on HashiCorp. So if I were to do this now, HashiCorp actually has a new version that will use DynamoDB on the back end to manage servers. So we're actually in the process of moving over to that. And finally, I want to mention AWS Secrets Manager is another thing that just was created last year to actually do this same thing in Amazon. All right, and here I just wanted to acknowledge some of the people who worked on our system and give them a shout out. And then finally, we have the links to our open source projects, Heaviside and BossDB. And we wanted to say thank you, and please fill out the survey. Any questions? Sure.